Okay, so we're going to look at a second mechanism for ionic addition, and in a question, if it was given in an actual organic synthesis scheme, it might look something like C2H4, and I'm going to change how might be written. It might be written as CH3 CH2Br. And from that, and again, we go back to basics. You draw out your scheme so you see what your molecule looks like. So it becomes CH3 CH2, and we've said any halogen or side group that we're putting on to the right hand side. So if I'm looking at this, we've broken our double bond, we have added on HBr is the reagent that we're going to use. So if I now have to describe, so in a question it might have describe the mechanism X, and from this diagram here you now know that mechanism X has got to be an addition, and it will be ionic addition because that's the only one you'll have done. So as we've said, I'm going to draw my reaction scheme going from left to the bottom and then up to the right, and we're going to just do a little bit of erasing to set us up. So here is going to be my very beginning, and over here when I get there, this will be my very end. But just to start us putting it all the way through and together, we will get rid of this. So the rules are, we've said here it has to be HBr is my reagent. Now HBr, if we were to look at it in terms of electronegativity values, and you were to take the numbers one from the other, you would find that it would fall between 0.4, greater than 0.4, and 1.7, less than 1.7, which makes it a polar covalent bond, and because it's only HBr, it also makes it a polar covalent compound. So when we draw HBr naturally, it will have a delta plus up here and a delta minus. So it's already polarized before it even gets next to an ethene molecule. But we still follow the rules for ionic addition. And the rules state that we have to put the HBr, so the delta negative part of our HBr, because it's already polarized, will be attracted to the double bond, and the electrons in the double bond will go for this delta positive hydrogen, and the electrons in your shared pair will go for the bromine. So this means then that in our second step we will make a carbocation, which now will have 3 hydrogens attached, so it doesn't really matter where we're going to put those because hydrogens are small, and we will now have our carbocation. So there's no other name for this intermediate. There's no bromine attached, chlorine attached. It is just a carbocation intermediate. And we've said in terms of the evidence, it is this thing that is key to proving that it's ionic addition. We'll talk about the evidence in a minute. So we have made our carbocation, and we now have our bromide ion, Br minus, it's a full ion, and these extra electrons are going to be attracted to the positive portion of our carbocation, resulting in the formation of our product. So we now have this molecule resulting after the end of our ionic addition. We always count our side groups from carbon 1. So the name of this molecule will be 1-bromoethane. And that is ionic addition for the addition of HBr to ethene. Our blurb hasn't really changed in that we will still have, you can still say that HBr has been polarized. It does it naturally, but HBr will become hydrogen with the delta plus, and Br with the delta minus. You can also say that there is heterolytic fission of your HBr into H plus and Br minus. So as we've said last time out, and every time we've talked about this, this is the step that is not shown. It's happening somewhere along here. We don't actually get to see it. It's inferred. Usually you will have enough in your 3 diagrams to get the marking points, but if you're going to write one piece of blurb, then this should be it. We are saying that, so I'll just get rid of here. For our step 2, to describe what's happening in step 2, our bromide ion is attracted to our carbocation, and it results in the formation of, in this case, 1-bromoethane. Okay, but as you've said, you get away with most of your marks for your diagrams. So in terms of our evidence, the evidence is always based on the carbocation. So the carbocation that we've made in this instant is going to be looks like this. So the type of question, again, they may say for this carbocation, give a piece of evidence that proves its ionic addition. So again, we want something that's going to have a negative ion. So it could be, you might have sodium chloride in your water. So we said the last time, sodium chloride, when it dissociates into Na plus and Cl minus. So then we're going to be interested in the Cl minus because the anion is going to go after the cation. Or we may have water in our solution. So we've said water, when it dissociates into H plus and OH minus. So in this case, the OH minus we would be interested in as our piece of evidence. So if we look at, if it was the chlorine, so we'd have our Cl minus down here, and our anion is going to go for here, making us Cl. We've said we put it on the side, always because the halogens, because they are large. So we'll just stay in that habit. This would become first carbon for our naming, so we would make 1-chloroethane, which is an unexpected product if we have C2H4 plus HBr as our reaction. Then this is unexpected, it shouldn't form. It does by ionic addition in the presence of, so ionic addition in the presence of chloride ions, of Cl minus ions. And then our second version would be if we looked at the OH. So if we had hydroxyl ions present, the anion is going to go after the cation, and we end up forming. So again, we're going to put our OH out at the ends, not drawing it on the same side as we do in organic, just because this is where our gap was. So what have we made now if it's an OH group attached? So in this case, we've made ethanol. And again, the reason for this is because we had Ia in the presence of OH minus ions, and again, ethanol would be an unexpected product. So I hope now that that makes you happier about our second ionic mechanism.